Hello! Today I'm going to talk about electromagnetic waves, or radio waves, or light waves. This is the third or fourth time I've tried to make this video, and even though it's not that difficult of a subject to explain, every time I've looked at the video after I've posted it, I've just been very unhappy with it. Sometimes I went a little too deep into things I didn't need to go deep into, and I keep finding other ways I think that are better to explain it. And so here we go again. I have made some notes to help me keep on track, which is something I don't usually do when I make my videos, but I'm going over basically 4 different areas and they're related. I want to be able to backtrack and show how they're related to each other. And so you'll probably see me looking at my notes a lot more than you do in other videos because I hardly ever use any notes. So when you see me glance down, that's what I'm doing. But hey, if Richard Feynman can do it, so can I. So here we go, one more try. And this video is going to be longer than I really like, but to cover the subject the way I want to, it's just going to have to be long. And after all, this is a video lecture. It's not a quick bite of information like you may see in a lot of places. So let's go ahead and get started. Now, one of the main problems I have with explaining electromagnetic waves is I have to get past something that is used everywhere to diagram electromagnetic waves, and it is this graph right here. This is very commonly used to explain what electromagnetic waves look like, if you could see them. And if you could see electromagnetic waves, they would look nothing like this graph, because after all, this is just a graph. It's a graph of the electrical and magnetic energy and the polarization, also showing the direction of travel. And if we could see electromagnetic waves, they wouldn't look anything like this. In fact, I find that people are confused by this because it gives the impression that electromagnetic waves are confined to some small area where these things are waving back and forth and up and down or whatever, and there's nothing waving back and forth and up and down. This is just a graph of the energy. So it's useful, but I think it's overused, and I'm going to try to explain what they would look like if we could see them and hopefully give a better insight into what electromagnetic waves are. So to start with, I'm going to talk about waves in general, and to begin with there, I'm going to talk about something that's not really waves, but we call them waves. So they're very closely related, but they're not the same. They're not physical, and these are signal waves. Sometimes they're called voltage waves, but you could argue that they're not necessarily voltage. And so what we have with a signal wave is, well, let's see if I can kind of make something. I'm going to put a battery here. In fact, I'm going to do 2 batteries just so I can have both positive and negative. So there's 2 batteries. I'm going to make them, let's make them 5 volts each. Positive to negative, positive to negative. And here is our ground, so that's where we're going to be measuring our signal from. And I'm going to take the ends and put them through a potentiometer. So there is that. So what do we know about that? We have plus 5 volts, 0 volts, and minus 5 volts. Remember that negative voltage is not the opposite of positive voltage. It's just a voltage that's lower than something else we've called 0. So by putting our ground here, which is also where we will put our black probe of our voltmeter or oscilloscope or whatever, and by definition, that is where 0 volts is. So what's 0 volts? It's where you put the black probe of your voltmeter, or it's where you put the ground lead of your oscilloscope. And that's the best explanation there really is, because wherever you put that, that's going to read 0 volts. And so this is going to be 5 volts higher than 0. That's going to be 5 volts lower than 0, a total of how many? 10 volts. So if I move this potentiometer up to that end, assuming that we're clamped all the way at the end, etc., we're going to see plus 5 volts. And if we move that potentiometer wiper down to the other end, we're going to see minus 5 volts for a total of 10 volts. And now I can start taking the knob on that potentiometer and moving it up and down. And I can make that voltage go up and down and up and down. So what we're going to do now is put that on an oscilloscope. So what is an oscilloscope? It is a voltmeter that tells us how voltage changes over time. So the vertical scale is volts, And we'll say it goes all the way to minus 5 volts. Let's put minus 5 volts right about there. I'll just put a little line and put another line there. So that's plus 5, that's minus 5. It goes a little further. And of course, our 0 volts is across the middle. And this is our time scale. And let's make it go across the scale, take 1 second to go all the way across that scale. So what I'm going to do is I'm going to turn that knob up and down and back up in 1 second. So what are we going to see? I'm starting in the middle at 0 volts, and I move it up to 5, back down to 0, to minus 5, back up to 5. And I'm going to keep on going, but we're going to just look at this part right here. So I've made 1 cycle. I can do that over and over and over again, have many, many cycles, but there is 1 cycle. So there's the definition of 1 cycle. And so I've taken 1 second to do that. So our time scale is going to be, to right there is going to be 1 second. We can modify the scale of our oscilloscope to be whatever we really need it to be. And so what we have is this wave. And what's the definition of it? It's a wave that takes 1 second to complete 1 cycle. That is the period of the wave. But as I keep doing that, how many cycles is that every second? Well, it's 1 cycle every second. So the period is 1 second. The frequency is 1 cycle per second. So what I'm going to do is I'm going to start doing that twice as fast. And so now what I'm going to get is it's going to go up and down and up and down and back up. So I'm doing it twice as fast, and I'm going to erase the original just to get that clutter out of the way. And so now what's happening? I'm going twice as fast, and so I have 2 cycles in the 1 second. So that's a frequency of 2 cycles per second. And of course today we call that hertz after Heinrich Hertz. So it's a 2 hertz frequency. And if I do that 3 times a second, I have 3 cycles per second, or 3 hertz. 4 times a second, it's 4 hertz. So our frequency, represented by a little cursive F, is our cycles per second. And if I do that 4 times every second, our frequency equals 4 hertz. So that's one parameter of it, is the frequency. Another parameter is the amplitude. So the amplitude is going to be how far I go above and below, or total movement of this voltage as we see it on the oscilloscope. So my amplitude is going to be a peak of 5 volts. So my peak amplitude is 5 volts, plus 5 volts, negative 5 volts, plus 5, negative 5. And my peak to peak, all the way from one to the other, is how many volts? How many volts is between here? Plus 5, minus 5, that's a total of 10 volts. In the AC class, we talked about RMS, which is a calculation where I take samples along this, take the square root, average them, and then square that, and I get a number, which is essentially what DC voltage would carry the same energy, if you will. It's maybe not the best explanation, but that'll do for now. And we want to look at the shape of this wave too, because what happens if I put a switch here and just turn 5 volts, minus 5, 5 volts, minus 5? We're going to get a 5 volts, minus 5, 5 volts, minus 5. And, well, it's kind of squarish, isn't it? We call that a square wave. And I can have other shapes of waves. We talk a lot more about that in the AC class, but just to say that they exist, I could have a triangle wave, which goes to a peak. So they're shaped like triangles, but we're going to be mostly interested in a particular shape, which is called a sine wave. I'm just going to erase this to make some room here. In fact, let's go ahead and get rid of all this. We don't need that right now for the time being. So the square wave looks pretty simple, on, off, but actually that's very complicated, and I'm going to explain how it is complicated in a minute. But before we do that, I'm going to show what's the simplest wave, which is actually mathematically complicated, but it is the simplest wave shape you can make. And that wave shape is what we would get if I take a round disc, and let's put a spot on there. There's a little spot there, I hope you can see it. And we're going to rotate that around. And as it rotates around, you see it makes a circle. And as it goes around, it goes 360 degrees, right? Now, if we turn that sideways to the camera, and I rotate that around, you really can't see it, but you can see my finger. If you see that rotating around, you'll notice it'll go rather quickly across the middle, slow down across the top, rather quickly across the back, then slow down across the bottom. But it will make a peculiar bouncing, kind of like on a spring, up and down. Now, if I take that and move it across your line of sight, we're going to see that make a spiral. Sort of looks like a spring on edge. And it will look edge on pretty much like this. So this is what's called a sine wave, because the voltage at any particular point is a function of the trigonometric sine of the number of degrees that dot has gone around the circle to make this. So as it goes around the circle and across our line of sight, it goes 90 degrees, 180 degrees, 270 degrees, 360, or back to zero. So we can measure the parts of this wave as degrees. And it makes this particular shape we call a sine wave, which again is any particular voltage is a function of the sine of the number of degrees we have gone through that wave. So that is what is called a sine wave. And the interesting thing is, if you have any other wave shape, you actually have multiple sine waves. The easiest one to explain is the square wave. So if I have this square wave, looks like this, looks a lot simpler actually, but we find that if we put some filters on there, that this square wave would have the fundamental frequency. So let's say this is 1 cycle per second, or it could be 100 cycles per second. Let's make it 100 cycles per second just because we can, or 100 hertz. So here's our 100 hertz sine wave, and this square wave contains that 100 hertz sine wave, but it also contains the third harmonic, or a frequency of 3 times that. So it contains 300 hertz at a lower power. So we also have 300 hertz. Let's see if I can do it 3 times here. 1, 2, 3. That's not bad. It also has 500 hertz. Can I do 5? 1, 2, 3, 4, 5. That's not too good, but it'll do. And then it also has 700 hertz. So notice it has all of the odd harmonics decreasing in amplitude as we go along. And so here is an animation of someone creating square waves by adding different frequencies of sine waves together. You can do this online. There's a Fourier synthesizer. I'll put a link to that in the description. A Fourier synthesizer makes different wave shapes by adding different sine waves. And so that's kind of important to know down the road when we get into communications and such. So if we have wave shapes other than a sine wave, we have a lot of harmonics in there. So for example, if we have a radio that's transmitting on a certain frequency, let's just say AM radio at 1 megahertz, and let's say that we're overdriving the output amplifier, so instead of getting a nice sine wave, it's getting flattened out on the top and the bottom. That means we're adding those odd harmonics to the signal, which means we're not just transmitting on 1 megahertz, now we're transmitting at 3 megahertz, and 5 and 7 at diminished amounts, but it's going to interfere with other people using those other frequencies. So it's very important in radio to make sure that you keep a pure sine wave coming out of your transmitter so that you are not interfering with people on other frequencies. So that is signal waves. Those are just changes in voltage. And a couple other things we need to look at about those. We looked at the frequency, which is represented by the cursive F. We also looked at the amplitude. I'll abbreviate that, which is how big the wave is. And we also looked at the period, which is actually the reciprocal of the frequency. So that's 1 over the frequency, and the frequency equals 1 over the period. So you notice when we had a 1 hertz wave that took 1 cycle per second, a 2 hertz wave is 2 cycles per second, and it's going to have a period of a half a second. A 3 hertz wave is going to have a period of 1/3 of a second and 3 cycles per second. And so frequency and period are reciprocals of each other. And another thing to look at is phase, because sometimes we mix different waves together. So let's say we have 2 wave generators. I'm just going to draw that as an AC generator here, and we'll ground it. We'll make another AC generator here, and we'll ground it. And we're going to run these to a summing amplifier, so it just simply adds them together. Now let's see what happens if we add those together. So let's say they're perfectly together. Let's say there it goes up and down and back up at the same time. If we put them on an oscilloscope, if I draw the oscilloscope over here, we have one wave up here and the other wave down here, and they're perfectly in sync. They are in phase. And if we mix them together, what's going to come out of here? Well, this is an additive amplifier, and what it's going to do is just simply add them together. So if this is plus 5 volts, and that is plus 5 volts, they're going to add together, and what's going to come out of here? Let's throw another image here. That's going to go, make it bigger. It's going to go plus 10, and of course then down to minus 10. And put volts there. So if we add them together, if they're perfectly in phase at the same time, we're going to get a doubling of the voltage. And here's an illustration of two waves. If you can kind of think of it as waves going down a rope, and you see where they meet, the amplitude adds together and it gets bigger, and then as they go apart from each other, they go back to their original size. I think it looks pretty interesting. There's a pretty good illustration of what happens when two waves meet. You may have heard of rogue waves out in the ocean. For many years, scientists didn't believe these exist, even though they'd been seen. I always figured they did, because what if some waves, we have waves all over the ocean and they come together and come apart. What if enough of that energy, just by chance, comes together at the same time? You're going to get a giant wave. And it turns out that they really do exist. And so that's when these waves come together, they can get very, very big. And of course, for each wave, there's a trough, and those troughs will get bigger too. So you end up with, if I get this out of the way here, I want to leave that on the board there for a minute. So if we have a wave coming together like that to another wave like that, when they meet, the peak is going to get bigger and the trough is going to get bigger. So you get those multiple waves coming together with a lot of peaks coming together. You're going to get a giant wave this way with a giant trough on both sides, or one side, or something like that. And so that's how waves will add together if they're in sync. So that's sort of what happens when they come together in sync. But what would happen if we inverted the phase of one of these waves? So this one's going up and down and up. This goes down and up and down. Put this back on our oscilloscope over here. Here's one wave here, and here's the other wave there. Now they're out of phase, and they're 180 degrees out of phase. Let's see what we mean by that. So there's our wave. Remember, this is 0 degrees. That's 90 degrees. Right there is 180 degrees. There is 270 degrees. And finally we get to the end, it's 0 degrees again, or 360. So if these two waves were, let's say the second wave starts right about there. So this one starts at 0 degrees and this one starts at 90 degrees. Well, those are out of phase by 90 degrees. So let's do that again. Here's the first wave, and the second wave is starting here. And so therefore it goes down and up there. Maybe I could draw that a little better here. So now it starts, instead of at 90 degrees, it's starting at 180 degrees. And so now, where this one's going up, that one's going down. Where that one's going down, this one's going up. So what's going to happen when we add those together? We have plus 5 volts here, and we have minus 5 volts there. What's going to happen when we add those together? What's going to come out of our amplifier? Plus 5 plus minus 5 equals 0 volts. So if these meet 180 degrees out of phase, so in other words, here comes those waves, but instead of a peak coming to meet a peak, we have a trough coming to meet the peak. It's going to just flatten out, and they'll actually subtract from each other. So it depends on how they hit. Peak to peak, they get bigger. Peak to trough, they flatten out and cancel each other out. So that is the opposite of a rogue wave, where you get I've never heard of it, but I bet they're out there sometimes. Yeah, look, there's a flat spot in the ocean where the waves just happen to meet such that a trough meets a crest, and you get a little bit of a flat spot. Probably very transient, but I'll bet you see them once in a while. I'd like to see if it's ever been photographed or if anyone even thought about it. But that's what would happen. So when waves meet 180 degrees out of phase, they cancel each other out. So that's what we need to know about phasing, and this will come into play a little bit later. So remember that when they come together in phase, they're going to add together. When they come together 180 degrees out of phase, they will subtract from each other. And of course, anything in between, if they're 90 degrees out of phase, they're going to add partly, and you'd have to do some mathematics to figure out exactly what that is, but we're not going to worry about that at this point. So those are signal waves, and they're not a physical thing, they're just changing voltage, but they are related to what we are going to talk about now, which are physical waves. And the first one we're going to talk about is surface waves, like waves on the ocean or waves on a pond, because, well, it's a good place to start, but also they sort of look like the pictures we get when we put these signal waves on an oscilloscope. So let's start by having a pond. Here's the surface of a pond. It's perfectly flat. There's no earthquakes, no wind, no nothing. And let's draw our ground out here. And I would like to illustrate this by dropping a rock in there and showing what the waves do, but I found that that's more complicated than is useful. So what I'm going to do is I'm going to make a little machine. Just put a little plunger here. Let's make that a spherical plunger. It's going to go into a machine that's going to just push that up and down and up and down. It's going to do it in a sine wave just to give the perfect wave that we need. So this is going up and down and up and down on a sine wave. When this pushes down, what's going to happen is going to push the water away. So let's illustrate that. And as it pushes it away, it's going to put pressure in the water. Now, when the surface was smooth, everything was in equilibrium. We had gravity pulling the water down, we had hydrostatic pressure pushing the water up, and everything was in equilibrium, but now it's out of equilibrium. We've pushed this down, we've tried to increase the pressure around it, and water is, they say it's incompressible. Technically, it's about 20,000 times less compressible than air, so for all intents and purposes, it is incompressible. So when we try to increase the pressure here, what's going to happen? It's going to push water up. And unfortunately, I haven't been able to find a really good illustration of this, but we're going to get something like this. Now, this wave is being pushed away, and so these crests are going to want to go this way, away from the plunger. And of course, now we're going to pull that plunger up. And as we do, we're going to let hydrostatic pressure push this trough back up. So that's going to go up. And of course, these have gone away, so they're maybe about here. And as this has gone up, that water has to come from somewhere, so it comes from the adjacent area. And so we get these two troughs. So as that goes up and down, we continually make this peak and trough and peak and trough, and we get these waves that go away. And they get smaller and smaller as they get away because it's spreading in a ring, and so the energy is being spread out. So what do we have here? We have these waves moving out. I'm going to just try to ignore it. I don't want to try to draw symmetrical waves here. So we're just going to look at the waves that are going to the right here. And of course, they are going out in a circle. So if we look at the pond from an oblique angle, we'll see that these waves are actually going out. We're looking down it obliquely, so it looks like ellipses, but they're spreading out like that. And what do we know about these waves? Well, they're traveling at a certain speed. We're going to assume that they're traveling at a constant speed. Just put an S here. Now, things can change the speed of these waves. Different waves travel at different speeds, and I certainly don't want to get into that because I am far, far from a hydraulic expert. But let's just assume that they're traveling at the same speed. So all the conditions are the same all through the pond, and these are traveling at a constant speed. Let's say they're traveling at, how about 1 meter per second. So that's the speed they're traveling out. And let's say this ball is going up and down 1 time every second. So in 1 second, how far are these waves going to travel? In 1 second, they're going to travel 1 meter. So every meter, we have a peak of one of these waves. So we have a new parameter here now. How far apart are these peaks? And that is called the wave length. And in electronics, that's represented by the Greek letter lambda. So we had frequency, represented by the cursive F. We had the period, represented by a small p. We had the amplitude, and the phase, often represented by the Greek letter theta. And now we have the wavelength, represented by the Greek letter lambda. And so that's how far apart they are. So what's going to happen if I start going up and down faster? Let's go up and down 2 times per second. They're still traveling at 1 meter per second. So if I'm making 2 of them every second, I'm going to have 2 waves for every 1 wave here. So I'll draw this down here. There's our 1 wave per second with a wavelength of 1 meter. And now I'm going to go up and down 2 times per second. So I'm going to go up and down and up and down. There we go. 2 times per second. So now in that 1 meter, let's measure it from here to here. In that 1 meter, how many waves do I have? I now have 2. So I now have a frequency of 2 hertz. And my period, I'm not really worried about that now because I want to focus in on what happened to the wavelength. Notice that now we have 2 waves per second, and they're twice as close together. So that's 1/2 of a meter. So as my frequency goes up, what happens to our wavelength? They got closer together. So as frequency goes up, we have our wavelength go down. And so we have a formula for that. So our wavelength is equal to the speed divided by the frequency. And likewise, if we know it, our frequency is equal to our speed divided by the wavelength. So they're reciprocals of each other. But the most important thing to notice here is that if we double our frequency, we cut our wavelength in half. Why? We have twice as many waves in the same space, so they're closer together. We have more of them. They're closer together. The distance is the wavelength, so the higher the frequency, the shorter the wavelength. And so if I go up to 4 times per second, 1, 2, 3, 4, through 5, you'll see there's a reason for that in a moment. So if I have a distance here of 1, 2, 3, 4 peaks in 1 meter, I now have a wavelength of 1/4 of a meter. So that's 4 times per second. I now squeeze 4 peaks in 1, 2, 3, 4 peaks in the space of a meter. And so now I have a wavelength of 1/4 of a meter. So once again, what happens if my frequency goes up? My waves are closer together, my wavelength is shorter. So that's something new we have with these surface waves, is our wavelength. Now there's some other things we can look at with these physical waves as we see them coming away from the ball. So here's our ball making the waves, and the waves are moving away from them. What do we have? We have, this has been pushed up. So it's up higher than the hydrostatic pressure would normally have it. So it wants to fall. It wants to let gravity pull it back down. So what we have there is potential energy. It's up there. It's not, at the moment that it's up here, it's not falling, but it has the potential to fall. So we can look at it like this pin here. I have this pin, and I could drop it, and if I did, as it falls, it has kinetic energy, the energy of motion. But as I hold it here, it only has the potential to produce that kinetic energy. But if I let go, then it went down. It now had the energy of motion, kinetic energy, which it imparted into the floor and vibrated the floor and created sound waves that we'll be talking about in a couple of minutes. So right now that has potential energy, and the trough is the same thing. We have hydrostatic pressure pushing up on it more than gravity is pulling it down, and so it wants to move up. So right now it also has potential energy and wants to convert that into kinetic energy. So what we have is a state where we have, at one point we have potential energy, and then when that finally falls, we then have kinetic energy. So in these physical waves, especially these ones on the surface of the water, we have a continual trade-off between potential energy, potential energy, kinetic energy. So that's what this kind of wave has, and we'll find that other waves have pretty much the same thing. So potential energy, and then turns into kinetic energy as it moves, and then it stops, but it has potential energy because it's overshot, has energy wanting to make it go back the opposite way. So kinetic energy, back and forth, potential energy, kinetic energy, potential energy, kinetic energy. And an interesting thing to look at, if we look at one water molecule right here, what's that water molecule doing? It's just going up and down. Kinetic energy, potential energy, kinetic energy, potential energy as the waves pass by it. And here's an illustration of what that might look like, although in reality it's going to make a circle, but we don't want to get that deep into it because we're not going to become experts in waves, but we're just looking at how these relate to electromagnetic waves. Now there's some other things we can look at with these physical waves, and that is how they behave. Let's look at some of the phenomena we can have with physical waves. So let's say we're looking down and we have some waves going across our pond, and we're coming up across, well, this could be out in the ocean, but whatever it is, there is a wall or something. So what's going to happen when these waves meet this wall? Well, they're going to go past it, but this part is not going to be undisturbed. We have a peak here and a trough here and a peak here and a trough, peak and trough. The water is going to want to move into that trough, so it's going to disturb this area here. So essentially what's going to happen is these are going to go around the corner. And that is called diffraction. So that's one thing that physical waves will do, is they will diffract. And that's when they go around an object. Sometimes it's called knife edge diffraction. Here's an illustration. Notice that the waves are going by the object and they are diffracting. But what happens if we increase the frequency? Well, these waves come closer together. There's going to be a little less space for this interaction to go along. And so we're going to get less diffraction at higher frequencies. So what is diffraction? That is how waves will curve around an obstacle. Lower frequencies will diffract more, high frequencies diffract less. So that's what we need to know about diffraction. And that happens with any kind of a wave, and here we have waves just going by a physical barrier. Another thing we have is refraction. So in this time, instead of having a barrier, what we're going to do is have a shallow area in the pool. So here we have a shallow area. I'm going to show the dots to begin the shallow area. So deep and shallow, and these waves are going to go faster in the deep area, but in the shallow area they're going to slow down. So two things are going to happen. When they slow down, they're going to get closer together. But more important is what happens if they come in at an angle. So let's erase these waves and bring them in at an angle. So let's say they're coming in like this. And now when we hit this shallow area here, the wave is going to slow down here. Now think of it like two wheels on a cart. Let's say there's two wheels on the end of this. Let's say that it's coming across concrete and hits sand. So it's going to slow down. So what's going to happen? This wheel wants to keep going the same speed. This wheel wants to slow down, so it's going to pivot. And this is pretty much what happens in this kind of a wave. In light waves, it's a little different. We'll talk about that down the road. But in this surface wave, it slows down, and so the whole wave, I'm going to show it hitting there, but it's going to pivot such that, let's make these a little more dramatic here. Let's come in at a good steep angle, just for dramatic purposes. Here comes our wave. It's going to hit that, and as it goes away, it's going to be shallower. So the waves are going to bend when they hit a barrier where they slow down at an angle. That is called refraction. So all waves do this if they go from one medium to another, where they slow down if they hit that medium at an angle. And we'll see that's very important to how lenses and stuff work, but it works with radio waves too, or with these surface waves in the pond. But that is refraction, where we're going fast, we hit some place where they're going slower, they're going to pivot and turn. They're going this way, then they're going that way. So they make that little turn right there. That's refraction. Okay, and the last property we're going to look at is, what if there is just a solid wall? So here's that solid wall. So what's going to happen when those waves hit that solid wall? Well, let's look at it sideways. Here's the wall sideways, and here comes the wave. And when it hits the wall, what's it going to do? It can't go through the wall, so it's going to push up, and that energy is going to push up. It's going to make that wave bigger as it hits the wall, because where can it go? And then that energy is going to come right back down. Where can it go? Only back the way it came. So it's going to push up, push down, and it's going to go back the other way. That is a reflection. So those are the three properties we want to look at here. Reflection. So diffraction is when waves bend around a corner. Refraction is when waves bend as they go from a medium with one speed to a medium with a different speed at an angle. And then reflection is when they hit another medium where they can't go through, and so the energy is going to pile up and then go back the way it came, and that's going to be a reflection. And another thing important about reflection, let's get this out of the way here. If these come in at an angle, what's going to happen? These waves are coming in at this angle. They're going to go out at another angle. what we see is that we have a direction coming in and a direction going out. Let me redraw this just for clarity. Here is our barrier that we cannot go through. The waves come in at this direction and then they go out in that direction. And if we draw a line perpendicular to that barrier, which is called the normal, we find that this angle, represented by the Greek letter theta, is the same as this angle. And so the angle of incidence, where the wave comes in, is equal to the angle of reflection, where the wave goes out. So here comes the wave in, and there goes the wave out at the same angle. So that is the other thing we need to know about reflection. So that is diffraction, refraction, and reflection, things that waves do. Now what happens if we have multiple waves interacting in this little pond here, or wherever we are? Well, we already have a pretty good idea of what's going to happen, because sort of the same thing that happens with the signal waves, and we already talked about rogue waves in the ocean. What's going to happen if two waves are going along? Let's say here's a wave coming this way and another wave coming, let's say, that way, and they meet each other. Well, here's that illustration again of two waves meeting each other. Where two peaks come together, they're going to, there's one peak, there's another peak. The result is a bigger peak. They're going to get bigger. But what about in between where they're lower? Well, the peaks get bigger and the troughs get lower. So that's what happens if a peak meets a peak or a trough meets a trough. But what's going to happen if they're out of phase? So let's say this wave meets that wave. Well, I drew where two peaks meet. Let me just redraw these waves. So we have one wave coming this way and another wave coming this way, and they cross each other. Well, there's two peaks meeting, and right here, remember the trough is in between the peaks, so there's a trough, there's a trough. Well, I'm in a trough there, so there's where two troughs meet there. So this is going to get bigger, taller. The trough is going to get lower rather than it would have been otherwise. But what about where a peak meets a trough? So we have a peak coming in to meet a trough. What's going to happen? Let's say this one's going up plus 1 foot, and this one's going down to minus 1 foot. What's going to happen when they meet? The peak is going to basically fill the trough, and they're going to be equal. So if we look at where two waves meet, and here's an illustration of two waves coming together, you can see that it forms a pattern. We can see where peaks meet peaks and troughs meet troughs. We get a lot of wave action, but in between there is no wave action. So if you look here in this illustration here, you can see that there are waves meeting each other, and we have dead areas where peaks are meeting troughs and leveling out the water so that there's basically nothing happening. So there's regions where there's no wave, and then there's regions where the waves are bigger. So we see here peaks are meeting peaks and troughs are meeting troughs, so we get bigger action. But then here we have peaks meeting troughs, and so the peaks are filling the troughs, and there's basically flat water in those places. So that's what happens when water waves meet each other. If two peaks meet, we get a bigger peak. If two troughs meet, we get a deeper trough. But if a peak meets a trough, we end up basically the peak filling the trough, and we just get a level area there. And so that's what the interference patterns look like if we have this in water on surface waves. The next kind of wave I'm going to talk about are compression waves. And that's what sound waves are. Right now I'm talking and I am causing the air to become more compressed and more rarefied, and that is traveling through the air, and that is sound waves. So sound waves are a really good example of what compression waves are. Another type of compression waves are the P waves of earthquakes. They travel through rock, and so it's actually compressing and expanding the rock, and they can travel at tremendous speed through the rock, and that's why earthquake warning systems, if you're far enough from the epicenter, the warning system will see that P wave, and that doesn't cause a lot of damage before the S wave, the back and forth wave comes, that does the damage. They might give you a bit of a warning. Now, there was an earthquake here a few weeks ago, And fortunately, it wasn't very big, but the warning came seconds before the main shaking came. But I know somebody who lives about 80 miles away, and they got about a 15-second warning before they felt the earthquake. But they were so far away, there wasn't going to be any damage. So I don't know how good these warnings might be. They might be helpful if it's a really, really big earthquake and the fault rupture hasn't reached your vicinity yet, but that remains to be seen. But anyway, those first waves coming from an earthquake are compression waves coming through the compressing of the rock. So here's an example of a compression wave. We have something compressing these, whatever they are, let's assume they're air molecules, and we get a wave going through, and then here it is just doing that over and over again. We have these compression waves going through this medium over and over, and you can see that the dots representing air molecules or whatever come closer together, and that increases the pressure, so they want to expand apart. So we have here, again, we have the compressing of the air, and it wants to expand. So we have potential energy, and as expanding, we have kinetic energy. But it's going to expand too far and become rarefied. So now it wants to come back together. The air around it wants to push it together, so we have potential energy again. So as these compression waves or sound waves or whatever they are go through this medium, we get compression where there's potential energy. They move out, we get kinetic energy. Then we get rarefication where we have potential energy again, and it goes back and forth between potential and kinetic energy again, just like the water waves did. So if we look at in one individual air molecule, you notice they only go back and forth, but the energy goes through the medium. Now here's another look at the same kind of thing. This is an illustration from Wikipedia I like, and this shows more of what a sound wave would be like, because sound waves are not typically confined into a box, although you could do it, but the sound waves are spreading out spherically. So when we had the surface waves, they spread out in a circle. Now we have a three-dimensional medium, so the waves spread out in a sphere. And so we have the compression and the rarefication, and so here's the source, and here's those waves spreading out. Compression and rarefication. So here's the pressure, rarefication, and this is continually getting bigger and smaller, causing those to spread out. So one thing we see here is that there's a gradient. High pressure, medium pressure, low pressure, medium pressure, high pressure. So there's a gradient between these. So if we took a pressure sensor and put it like right here and ran that to an oscilloscope, what would we see? We'd see the pressure go up, the pressure go down, the pressure go to a vacuum, if you will, of negative pressure, and go back up. Oh, that looks familiar. This would produce that same signal that I produced by doing that potentiometer, or more realistically, to do it with an oscillator that would actually automatically create these waves. But notice the pressure has a gradient, just like the waves that we had of the signal waves had this voltage gradient going up and down and up and down. Pressure is going up and down and up and down and up and down. So we can graph the pressure in here a lot like we could graph the voltage. And we could see that that pressure gradient is at any point, we can see that pressure going up and down as this wave expands spherically. So let's say we put a number of pressure sensors along here. What would we get? We would see that the pressure gradient of the sound wave is going to be up and down and moving in one direction. So there we are graphing this sound wave. So the pressure goes up, down, and it's moving in this direction as I showed that. We don't usually look at sound waves like that. We don't usually graph them like that, but I'm leading up to that graph of the electromagnetic waves to show you what it really represents. So this is representing the pressure along that plane being represented by this sine wave going up and down as it reads the different pressure sensors. So this is one sensor. We would see this wave. We can see that there's a peak there and a peak there and a peak there and a peak there, and these are all traveling in that direction. And so we could graph that as pressure is going up and down and moving in that direction. So that's what we could look at, seeing that pressure gradient there. So what else do we have in sound waves? Well, we have frequency, just like any other wave. So if we have that source expanding and contracting faster, we have a higher frequency. So if it's expanding and contracting 1 time every second, that's a frequency of 1 hertz. And if it's expanding and contracting 2 times a second, we have a frequency of 2 hertz. And how fast are those waves traveling? Well, it depends on the temperature and the altitude and a few other things. But let's just assume they're traveling at 1100 feet per second, so it's a regular speed. So they're traveling at a particular speed, so I don't know off the top of my head what these wavelengths would be, and it's really not important at this point, but if they're traveling at a certain speed and they're a certain time apart, we have a particular wavelength, right? So if they're traveling at 1 meter per second, which of course they're traveling at 1100 meters per second, but let's just make some easy math. If they're traveling at 1 meter per second and we're making one wave every second, then what's the distance between these peaks? 1 meter. So that would be our wavelength. What's going to happen if we double the speed that ball is expanding and contracting? Well, now there's going to be twice as many of these. Did I draw twice as many right? And so that would now give us a wavelength of 1/2 meter. And if we double that frequency again, we'd have a wavelength of 1/4 of a meter. So once again, as we increase our frequency, our wavelength goes down. If we have that ball expand and contract at one speed, there's our waves going out. Let's say it's expanding and contracting at 1 time per second. But if it expands and contracts at 2 times per second, we're going to get twice as many waves in the same space. That puts them closer together, so the wavelength is half. So basically the wavelength would be the distance between two peaks of the pressure gradient. So these are the peaks of the pressure gradient. They're so far apart as they travel away, but if we double the frequency, we squeeze more peaks into the same area, so we have half the wavelength. So once again, doubling the frequency cuts the wavelength in half. Another thing about sound is we can hear it. And so lower frequencies are perceived as lower pitches and higher frequencies are perceived as higher pitches. So the lowest frequency we can theoretically hear is 20 cycles per second or 20 hertz. And the highest frequency we can theoretically hear is 20,000 hertz. And so our frequency range is 20 hertz to 20 kilohertz. So those are perceived as pitches. And if we double the frequency, we go up 1 octave. So if we have an A440, 440 is the A, what would be A80? That would be an octave higher, it would be another A. And so that's how we perceive sound. All of the other things we talked about, what about diffraction, refraction, reflection? Do those all work with sound? Well, how about diffraction? Well, let's say we have a brick wall here, and I have somebody talking over here. And as they talk, blah, 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 the sound waves are going to come, and if I'm trying to listen over here, am I going to be able to hear them? Probably, because the sound is going to diffract around that wall. The higher the frequency, though, the less diffraction. So low frequencies are going to diffract. I can hear them just fine. What about high frequencies? Double the frequency. Let's really make the frequency a lot higher. They're not going to diffract as much, so I probably won't hear the higher frequencies. And the intelligibility of sound, especially speech, is carried in the higher frequencies. So if I'm standing up here and he's talking, I hear every word he says. But if I go behind that wall, I can still hear him, but he sounds like mum, 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 because I can't really hear the high frequencies that define the consonants that make him audible. So we do have diffraction around walls. You've all heard it. Someone talks to you from the other room, you can't hear a word they're saying. And that's because the high frequencies are not reaching you, but the low frequencies are. You can hear them, but you can't tell what they're saying. So that's diffraction with sound. How about refraction? Will sound refract? You bet it will. A good example we have here in Southern California are Santa Ana winds. In the fall and winter, we get these conditions where the winds turn around, and normally we get our winds coming from the ocean. But in the fall and winter, sometimes we get this low pressure area in the Great Basin that causes the winds to come from the east. And so this warm, dry air comes down, and we have hills, foothills here, and this wind comes down, and here comes that warm air, trapping cold air in the valleys and warm air above. Sound travels faster in the warm air than in the cold air. So let's say there's a freeway over here. There's cars and trucks and buses and everything. I'm standing over here. Now, normally I don't hear that because the sound just goes on, and I might not hear that because, especially if there's stuff in between me and them. But when we have the Santa Ana, what happens? The sound travels faster in the warm air, so it travels up, And remember what happens with the water waves when they went to a medium with a speed change? They're going to go faster there, so it's going to pivot around. So the sound that goes into the warm air is going to pivot around and bring it back down. And so during a Santa Ana, these sound waves refract back down. And so one of the things I know, if I go outside and I can hear the freeway, we're having a Santa Ana today because I can hear that temperature inversion. Very common. I have a friend who said, I don't hear that. I hear just the opposite. I live up on this hill. So my house is, I'll put it all the way at the top. Now what's going to normally happen, he normally hears that traffic, doesn't he? But during the Santa Ana, that sound is bent back down to me. He says, I get just the opposite. Normally I hear the freeway, but when there's a Santa Ana, I can't hear it. And I said, here's why. Because normally that sound comes up to reach you and you can hear it. But during a Santa Ana, it refracts back down to me, and now I hear it instead of you. So sound does refract. Does it reflect? Of course it does. We've all heard echoes, sound reflecting off of a wall or a cliff or whatever. And so that's the same thing with the water, except instead of the water going higher with the wall in the water, we had said that the water hits there and the energy pushes the wave higher, it comes back down and pushes away. With sound, what happens? It comes and hits the wall and it compresses against it and then expands and goes back the way it came. So we get reflection in sound too. So sound being a wave, it diffracts, it refracts, it reflects. So sound diffracts, refracts, and reflects, just like surface waves. So the next thing I want to talk about is electromagnetic waves. And so there's a number of ways to create these. I'm going to look at what I think is the best one to start with, and that is to go out into space and just have a wire that is 150 meters long. Just a straight piece of wire. And what I'm going to do is attach a battery, negative side of the battery, to this end momentarily. And I'm just going to have a little wire coming around here, and that will electromagnetically couple over to here so we can get a full circuit. It's a little complicated. We'll hear more about that when we talk about antennas. So that'll couple around such that we can actually get a circuit so the electricity can flow into that wire. So what's going to happen when I put that negative terminal on this wire? Well, that wire, of course, has lots of free electrons, like any wire does. And this negative potential, these electrons here, are going to push against them. So it's going to push all those electrons up against that end of the wire. That is going to push them up there, and they can't escape, so they're going to compress together, and they're going to want to push apart. So what do we have? We have, sounds like potential energy. It sounds like they'd really like to go back the other way. So we're going to leave that there momentarily, and we're going to take it away. And now without this battery pushing the electrons up this way, I'll just show a whole bunch of dots around here concentrated up there. We have that potential energy. They're going to turn around and they're going to run this way. And now we have a current flowing in that wire. And as the electrons are flowing through the middle, we have that current, and they're going to overshoot, and now they're going to bunch up on this side. And so now we have a voltage gradient. Before we had a voltage gradient, negative to positive. Remember, more electrons, fewer electrons. That's what the difference between negative and positive is. They're not opposites, but just differences in amount. But that is flipped now. Now that's negative to positive. And now we have potential energy again, and they're going to want to go back this way, creating kinetic energy. And so we're going to have a current going back and forth in that wire. And it would go back and forth indefinitely, except for a few things that happen, one of which we're going to mention in just a moment. What do we know happens when you have a current in a wire? You get a magnetic field around that wire. So as these electrons are traveling, we get a magnetic field that builds up as more and more of these electrons go through the middle. But then as they go to the other end and bunch up, that magnetic field is going to collapse because the electrons aren't moving anymore. Then what's going to happen is they're going to go the other way, so we get that magnetic field build the other way and then collapse. So this magnetic field build and collapse, build and collapse. Now don't look at these electrons like a platoon of electrons going back and forth. It's more like a spring. In fact, maybe even a better analogy I like is water sloshing back and forth in the bathtub. It goes this way, gravity pulls it back down, so it goes across and goes this way, back and forth. Think of the electrons just kind of bunching up this way, equalizing out, but they overshoot, then bunch up this way back and forth. So as this magnetic field builds and collapses and builds and collapses, it disturbs the equilibrium of the space-time continuum. Remember, in the pond we had that equilibrium. I didn't talk about equilibrium in the air, but we could have. But in the pond we had the equilibrium, then we disturbed it, we got waves. Now we have equilibrium and we disturb it with a magnetic field, we get waves. So as that builds and collapses, we have electromagnetic waves moving out into the luminiferous ether, or, well, the space-time continuum. And of course that's dissipating energy, because what is that? That's power. Power, remember, is the production of heat, motion, or electromagnetic radiation. And there goes that electromagnetic radiation. So I take the battery off, the electrons go back and forth a few times, then they stop. And early radios pretty much worked like that. You would just repeatedly get those electrons going back and forth inside that wire. Okay, so why did I choose 150 meters? Because that gives us some numbers that are easy to work with. So let me erase this and redraw it. So we're making an assumption here that at 150 meters, the length of this wire, that these electrons are traveling at the speed of light. Of course they're not. The wave of energy is traveling close to the speed of light, but not quite. And so in reality, antennas are physically shorter than electrical length. So if this was a real antenna, it would be a little shorter than 150 meters, but we're going to assume that this wave is going back and forth in this wire at the speed of light rather than something like 95% in reality. So at 150 meters, how long is it going to take for that wave to go from one end to the other and back? It's going to take 1 microsecond, or 1/1,000,000th of a second, which means if it's taking 1/1,000,000th of a second to complete one cycle, how many cycles per second is that? That's 1,000,000 cycles per second. Or as we would say today, 1,000,000 hertz, or 1 megahertz. So we are creating radio waves at a frequency of 1 megahertz by getting those electrons to go back and forth in a 150 meter antenna. Now if we put this on the Earth, we need to shorten it to 75 meters about, and that gets complicated. We'll talk about that in antennas in the communications class, but we're just going to stick with the 150 meters here because that makes things easy. So we know we're producing these at 1 megahertz. How fast are these waves moving away? Well, we know that electromagnetic waves move at the speed of light, which is just a tad under 300 million meters per second. It's actually 299. It's one of these numbers I need to memorize because it's a constant that's used to measure a lot of other things from, but we'll just assume it's 300 million meters per second because it's very close. It's just short of 300 million meters per second. So those electromagnetic waves are traveling away from that antenna in a spherical manner. Well, not quite, but we'll talk about that in depth in the radio class. So these electromagnetic waves, like the sound waves, are moving spherically away from that antenna at a speed of what? 300 million meters per second, or the speed of light, represented by the letter C. So what is the nature of these radio waves that are radiating from the middle of this antenna? And that's kind of an important thing. Radio waves tend to come from the middle more than the edge. That's just one thing. If I want to be really accurate, that's not a sphere. I need to have what's called an isotropic radiator to make a spherical wave. But we'll just assume that this will, because it doesn't really radiate much off the ends. That's antenna stuff we'll talk about down the road. So let's just assume they're coming out spherically. So what is the nature of these waves? Well, what we have is electric fields in a sphere. So let's erase this and just draw a circle representing a spherical electric field. So there it is. It's kind of like a bubble. And it's going to have an electric property such that, sort of like a pole of the Earth, we're going to have it, let's just make it positive on one end and negative on the other, this particular sphere that's expanding away from that antenna, which is somewhere in the middle. So if we are here, and we take a voltage sensing piece of equipment, probably a voltmeter would not be adequate for this, but we would notice as we go up, we get more positive, more and more positive, until we get a peak positive there. Then as we go this way, we get more and more and more negative. And so remember, negative is not the opposite of positive. And so we have positive here, lower, lower, and lower, and lower till we get the lowest point here, which is what we call negative. So our gradient is that way, positive to the top, negative to the bottom. If we happen to be over here, of course, we see positive that way and negative that way. And wherever we are around that, we see positive toward the top and negative toward the bottom. What if the antenna was rotated 90 degrees? Well, the sphere would be the same thing. I'll just draw that over here. Now the positive here, negative there. And so that's going to be rotated depending on what the source was when it created the electromagnetic waves. And we call that polarization. That's something that sound doesn't have. Polarization depends on the orientation of that electric field. Is it vertical or horizontal or somewhere in between? So the polarization is the orientation of the electric field, and we'll call it usually either vertical or horizontal. If the electric field is oriented vertically, positive to negative or positive to negative, then it's a vertically polarized wave. But if we turn it sideways, where positive is left and negative is right, or vice versa, then it's a horizontally polarized wave. So that's a new thing. We have polarization with electromagnetic waves. So that's an electric field. But because that electric field is moving, what do we have associated with it? A magnetic field. So that magnetic field goes around basically the equator. So I'll draw that this way, and I'll just draw some dots going around the other side. There's that magnetic field going around horizontally if the wave is polarized vertically. It's a little different because we don't have north and south on opposite sides. It's basically like a bunch of little magnets. So if we take a magnet, north, south, and we break that magnet in half, what do we get? We get a north half and a south half, right? No. Now we have two magnets. And if we break it again, we have four magnets, or three or four. So that's the way magnets work. And that's the way this works. It's basically a whole bunch of little magnets end to end, and then think of it just one long magnet. North is that way, south is that way. And if we could break it up, we'd have a little north, south, north, south, north, south. Think of it as a whole bunch of little tiny magnets. North, south, north, south, north, south, as it goes around. And of course, if we flip it over, so this is positive and that's negative, then the magnetic field flips with it. So we have the magnetic field going around the equator and the electric field going pole to pole. And that magnetic field actually sort of like latitude lines, and it gets weaker and weaker to where it's no magnetic field here, strongest magnetic field, and as we go down toward the negative side, it's sort of like the latitude lines on a globe, and they get weaker and weaker and smaller until we get to that end. So electromagnetic wave, think of it as an electric field that's positive on one end, negative on the other, with a magnetic field going around the middle. So if I measure it here, I'm going to see that I have so much negative energy, and my magnetic field is still going to go around horizontally, but it's going to be a little weaker. So it gets weaker and weaker as we go to the poles. And that's what this electric field looks like. But of course, what is that electric field doing? It's expanding. How fast is it expanding? Well, its radial expansion is the speed of light. So this whole thing is expanding out in all directions at 300 million meters per second, or c, the speed of light. And so what do we have right behind that? Well, I'm going to cut this in half. We're trying to look at it three-dimensionally there. So here's our source, and we have multiple electric fields expanding away at the speed of light in all directions. So that's what that electromagnetic wave is doing. It's just spheres of electricity and magnetism expanding and expanding one behind the other. As I make more and more of them, I get more of them. And so if we look at each one of these shells, let's say this outer one here is going to be negative at the top, positive at the bottom. And then the next one is going to be positive at the top and negative at the bottom. So what we want to do, let's put a sensor here and watch these go by. What I'm going to see is the electric field is going to get stronger and stronger and stronger, weaker and weaker and weaker, and there's nothing. So that's like between here and here, strongest field, weakest field. And then it's going to reverse polarity. There's that graph again. So that's going to be the negative. Let's draw it the opposite way since I started with a negative. There we go. So it goes negative. So that's the strongest point, but as this goes by and the next one comes, it's going to get weaker and weaker and weaker. So I have a gradient to where I get halfway between. Here's my sensor right there. Halfway between, I'm at no voltage whatsoever. And then as it comes to the next one, it's going to get more and more positive until that one reaches me. And then I have a gradient where it's going to go down, down, down to nothing. And then it's going to go negative again. So the next one's going to be negative and positive. Hope I can keep these straight. So that's going to be negative up, positive down, positive up, negative down, negative up, positive down. And the strength is going to get more and more negative, less and less negative. In between, zero. More and more positive, more and more positive till I reach the peak. Then less and less positive till I reach the middle. Neutral, nothing there. Then more and more negative until I get there. And then middle, and it's going to go over and over again. So there's a graph of the energy density as these waves come at me. So it's not just a bubble front, but my field is the strongest at one point, then it's going to get weaker and weaker and weaker as that one goes away. Then here comes the next one, stronger and stronger and stronger, strongest. Opposite polarity, weaker and weaker and weaker, weaker as it goes away. Then there's nothing. Then here comes the next one, stronger and stronger and stronger and stronger. Negative top, positive bottom. Goes away, gets weaker and weaker and weaker as these pass by me. So these bubbles, if you will, are passing by me, but remember it's a gradient. And so just like the sound waves, we get this gradient in there. So there's that part of that graph that I don't like, although it is accurate. People like it, and it's useful, but it gives people a wrong impression that this electromagnetic wave is not confined in some space here, but it's actually an expanding bubble. What's the other half of that graph? Well, remember we have a magnetic field too. So that magnetic field is strongest now, weaker and weaker and weaker. Now it's gone. Now it reverses polarity, gets stronger and stronger and stronger. So I'm seeing as those electric fields come by, strongest electric field, strongest magnetic field. The electric field is this way, the magnetic field is that way. Then as it passes by, it gets weaker and weaker and weaker. There's no more magnetic field. Then it starts to build again. Opposite polarity. They're going around the other way. Gets stronger and stronger and stronger. And at the time this voltage is at my greatest positive voltage, I have the greatest magnetic field in the opposite polarity. And then that drops back down. So I have these gradients coming. So since the magnetic field is perpendicular to the electric field, and here we have vertical polarization. Remember, if the electric field is vertical, it's vertical polarization. If the electric field is horizontal, it's horizontal polarization. So we have this vertical polarization, and so the electric field is vertical, but the magnetic field is horizontal. Oh, look, there's that drawing again. So if I put that up here, let me erase this so we can see it. So there's that drawing that I don't like, but now we've explained exactly what it is. Basically, we have a probe that's looking at the electric and magnetic properties at a particular point as this wave goes by. It's going by in this direction, but I'm seeing the electric field get more and more positive, less and less positive, more and more negative, less and less negative, creating this voltage curve. But perpendicular to that, in this case horizontal, we have the magnetic field, north to south, south to north, north to south, and south to north. And so that is what that is showing us. But as you can see, it's an expanding bubble rather than something waving up and down and waving back and forth, which it is not. So now you can understand what this graph is trying to explain. So electromagnetic waves basically go everywhere. They don't tend to travel from one point to another, somehow knowing which way to go. So here we have a bit of an illustration of these fields expanding with their gradients. And this looks a lot like the sound wave because it should. The sound wave is pressure gradients. The electromagnetic wave is electric gradients and magnetic gradients. But remember one thing. What is a magnetic field? It's an electric field viewed from a different relativistic frame of reference. So really it's an electric field. The magnetic field is something that's perceived because of relativity. But we can measure the magnetic field, so there it is. So let's get back to our antenna, which is 150 meters long. And so the electron wave is going back and forth 1 million times every second. So it goes up and back, millionth of a second, up and back another millionth of a second. So we have a frequency of 1 megahertz. Now the electric wave is moving away at what speed? The speed of light. We'll just call that c, but of course we know that is approximately 300 million meters per second. So at 1 megahertz, how many of these waves are we creating every second? 1 million. And they're going at 300 million meters per second. So how far, let's just erase this for a second here. Leave those numbers up there. Here is our antenna off in the distance radiating these waves. And let's just keep it the way it was. I'm going to draw one more ring here. So they're traveling in this direction. And this is our positive to negative, positive to negative, positive to negative, positive to negative, no, positive to negative. Okay, so here's one peak, positive peak. Here's the other peak, a negative peak. And then here's the other positive peak and negative peak. So what is the distance between here and here? Positive peak to positive peak. We have 1 million cycles per second traveling at 300 million meters per second. I'm asking what is the distance between these two peaks? That is going to be 300 meters. So there we have wavelength. Radio waves have wavelengths. You've probably heard of them referred to by their wavelength. So we might talk about their frequency, or then we might talk about their wavelength. Just like other waves, frequency is equal to the speed, which is now the speed of light, over the wavelength. And the wavelength is equal to the speed of light over the frequency. So they're reciprocals of each other. So if you know one, you know the other. So at 1 megahertz, we have 300 meters apart. So those waves of a 1 megahertz signal, which is in the middle of the AM radio band, those waves are 3 football fields apart. I don't know how big a soccer pitch is, but they're about the same size. So you can figure out how far apart. Here's one peak. There's the trough. There's the next peak. So there we've got, what? 3 football fields. There's the goalposts. So there's how far those are apart. Pretty big. What about lower frequencies? Yeah, they even have a bigger wavelength. And we talk about radio bands by their wavelength. And we call this medium wave in the wavelengths we use for AM radio broadcasts. But we also have long waves and super long waves. I'm not going to get any deeper into this because that's for the radio class. But we have different bands that we represent by the number of meters. So let's give an example. In ham and CB radio, I used to be in the CB radio when that was a thing. That was the 11 meter band. Right next to that was the 10 meter band. So the 11 meter band, meaning our waves are 11 meters apart, that's going to be 27 megahertz. The 10 meter band is going to start at 30 megahertz. So this is a ham radio or amateur radio area. This was or still is, the citizens band, at least in the United States, operating in 27 megahertz area, and the 10 meter around 30 megahertz area. So we may call it the 10 meter band, or 30 megahertz, or we may call it the 11 meter band, or 27 megahertz. As we go lower in frequencies, we have very low frequencies, ultra low frequencies, and such. But as we go higher, we also have different names for these bands. So let's go back to our antenna and see what kind of things we can find out about that. So here we are back in space with our 150 meter antenna. And so it's producing radio waves at 1 megahertz. Now, of course, what we have is a generator attached to that keeps feeding the energy in, otherwise it would dissipate. But we want that antenna just the right length so that when this is pushing out, the electrons are ready to go. So they go out and come back, and just when they're getting their potential energy ready to go, this gives them a push. And so that's basically what that does, keeps putting the energy in. But we're just going to look at the antenna. So what's going to happen if we cut this down to 15 meters. What's going to happen to the frequency? Well, if we cut that down by a factor of 10, the frequency is going to go up by a factor of 10, so that's going to be 10 megahertz, which would also be called the 30-meter band. And do people operate at those frequencies? Of course. If they operate at 1 megahertz, they certainly operate at 10 megahertz. The amateur radio has a number of different bands they operate with different characteristics, which we will talk about down the road. What happens if I shorten that down to 1.5 meters? Getting awfully short there. That's going to end up being 100 megahertz. In amateur radio, we have the 2-meter band, which is around 150 megahertz. So let's make this 2 meters. It's going to be roughly 150 megahertz. So the higher the frequency, the shorter the wavelength. So we're getting down here to the 2-meter band. Instead of having wavelengths that are 3 football fields across, now we have wavelengths that are about as tall as me, if they're going up and down, so about approximately 6 feet or 2 meters, depending on where you are in the world. And as we go up and up in frequency, we get even shorter wavelengths. I have a few here just to talk about. Okay, microwaves. You've all heard of microwaves. We're talking about 300 megahertz to 300 gigahertz. So what's the wavelength going to be at 300 megahertz? That's going to be 1 meter. So at 300 megahertz, we're going to have 1 meter wavelengths, so about that big. But then we go to 300 gigahertz, we're going to have 1 millimeter. How about microwave ovens? You all have those? What frequency do they work at? I'll have to take a quick peek at my notes here. 2.5 gigahertz, because that particular frequency vibrates the water molecules. It twists them around and causes them to heat up, and that heats up our food. So as we get higher and higher frequencies, we eventually get out of radio and we get into infrared. But we're not going to talk about that just yet. We just want to look at radio waves. Do they have those same phenomena that other waves do? Do they refract? Do they reflect? Do they diffract? You betcha they do. So for example, if I have a hill and I'm over here with my antenna, low frequencies will diffract around that hill and I can pick them up with another antenna here. But I get out with my little 2-meter handheld with the shorter wavelength and no dice. They do not refract around. So just like other diffraction, the lower frequencies diffract more than the higher frequencies. So my little handheld is line of sight, and I don't operate in other frequencies. I'm not big into ham radio. I just have a little 2-meter unit. But people that operate at lower frequencies can go right over those mountains. They can curve around the earth and they can bounce off the ionosphere, all sorts of things they can do. Oh, how about that? Reflection. There's a layer above the earth called the ionosphere. So there's the earth, there's the ionosphere, and 11 meters is really good at this, especially in the daytime. I have my transmitter over here, and it's not going to go very far around the curve of the earth, but it will reflect off the ionosphere and come back down. And I can hit people pretty far away. This area here is called the skip zone. Once again, not to get too deep into that, but you hear people talk about the skip. What they mean is that they're going over the skip zone and they're able to transmit from this point here to this point here, even though it's over the curve of the earth, because the radio waves reflect off of the F2 layer of the ionosphere. And that's about all I know about the ionosphere. There's a layer called the F2 layer, and 11-meter signals reflect off of that. Yes, they will reflect. They will diffract. Will they refract? I don't know of an example off the top of my head about low frequencies refracting, but of course when we get into light, we do have refraction. We'll be talking about that in just a moment. Which brings us to the next kind of electromagnetic radiation, which is light. So how do we produce light? Well, I'm going to talk about a couple of different ways to do that. The first one I'm going to talk about is what's called black body radiation. I'll explain what a black body is later, because it might be a little confusing if I explain it right now. But black body radiation, let's just assume that we have, just a sphere of stuff. It doesn't really matter what the stuff is. It could be a ball of iron, it could be a ball of rock. But if it has a temperature of absolute 0 degrees Kelvin, or 0 kelvins, it will produce no radiation whatsoever. But if I am greater than 0 degrees Kelvin, electrons in this will start to vibrate. And what happens when electrons vibrate? They produce radio waves, don't they? And so at very, very low temperatures, this object, doesn't matter what it is, and it depends entirely on the temperature, will start to produce long wavelength radio waves. And I don't know off the top of my head what temperatures produce different radio waves, but we will get to some when we get into the light. So as that gets warmer and warmer, it starts to produce more of this. And it's kind of random. It's not like a radio station where we get these nice coherent waves working together. It's just kind of chaotic. But anything that has a temperature above absolute 0 produces radio waves. So as this gets warmer, there are more energy states for these electrons to go to. So we get more radiation of more frequencies. So it's very broad spectrum. It's not like one frequency. It's not a single frequency per temperature, but we get a broad spectrum. And the higher the temperature, the higher the frequency that this peaks at. So we get something like this, some radiation peaking at a particular temperature. Let's say it's going to be 100 meters. At a higher temperature, it's going to peak at some other wavelength. So we get a lot of different frequencies, but they're going to peak at a particular frequency depending on the temperature. And somewhere in my notes, I actually have the temperature. Where is it? I just noticed that my printer doubled up one page and I'm missing another, and so I don't have all my notes here, so I'm winging it from here. But our bodies are roughly this temperature on the Kelvin scale, and at that temperature we are producing infrared radiation, far infrared radiation at this wavelength. So you are producing radio waves right now. Anything with a temperature above absolute 0 does this, and it's called black body radiation, which means that this body will absorb any energy that comes to it. So any electromagnetic radiation that hits a black body is absorbed and just simply raises its temperature. And the radiation coming away from it is 100% dependent on the temperature and nothing else. The sun is a black body radiator. So we think the sun's a black body. Well, it's producing its own energy. It's got a lot of heat, but it's going to produce energy which peaks at this wavelength here, but of course it's a very broad spectrum, so the light coming from the sun is very white, but peaks at this particular wavelength, and it is a black body radiator. It has that broad spectrum of any other black body radiator. When that black body radiator gets up to a temperature of 2857 kelvins, or 2857 degrees Kelvin, it now produces radiation at a wavelength of 700 nanometers. Which is the edge of visibility. Now, of course, you're going to be able to see it before that, because remember, it's a very broad spectrum. So long before it gets up to that temperature, it's already producing some radiation at this wavelength. But when the body gets up to 2857 degrees Kelvin, it peaks at this. And so it's starting to produce very bright, visible light in the deep red zone. Of course, it's producing a broad spectrum. So that's going to be at 2850 degrees Kelvin. Once we get up to 7500 kelvins, now we're at 400 nanometers. So now we're getting up into the infrared range. And so somewhere in the middle is something like the sun producing this white light. So this is going to tend to be bluish. That's going to tend to be very reddish. The sun is about halfway between, producing very white light, a very broad spectrum. And this is why when we talk about broad spectrum light sources such as the sun, but especially incandescent lights, we talk about degrees Kelvin, because it's a broad spectrum and it peaks at a particular temperature. And each one of these will have a different character. I don't know the numbers off the top of my head, but I'll move over so I can put them here. If you look at LED room lights, you'll see that they have different degrees of Kelvin temperatures to tell you what kind of color they will be. So we get one temperature is going to be warm white, another temperature is going to be slightly different, maybe not as warm, but we get to the higher temperatures, it starts to get into the blue range, starts to produce bluish light, bluish white light, And so they call that cool white. And so when we look for our LED lights, we look for either the warm white, cool white, or what we want, but we'll notice that each one of those is associated with a different temperature of Kelvin. So when we're talking about broad spectrum lights, we talk about their color temperature. Now when we get to light of 1000 nanometers, I don't know off the top of my head what the color temperature of that would be, but I'll just stick it up there for now. But this would be a frequency of 300 terahertz. So this is fairly near infrared, 1000 nanometers. You can't see it. You can see beyond 700 nanometers because our eyes are sensitive into the infrared range. The 700 nanometers is just where our eyes are 50% as sensitive as at the peak. But we cannot see this, but that would be 300 terahertz. So I just think that's interesting that that's a particular wavelength associated with a frequency. So light does have frequency. As we go up to 700 nanometers, what's the frequency of that? I'm not going to calculate it, but remember, our frequency is equal to the speed of light over the wavelength. So can I calculate that out? Sure, there it is. So at 700 nanometers, that's the frequency. And at 400 nanometers, that's the frequency. I can calculate it out and give you those numbers and put them on the board just like that. So what else do we know about light? That's the basics of it. Does light diffract? It's electromagnetic radiation. It's waves. Yes, it diffracts. You can see that in shadows. Here's a picture of light going past a razor blade, and you can see that there's little fringes because of the diffraction. So it does diffract. It does reflect. Does it refract? Of course it does, going through glass. It changes the speed. So as we go from air to water, light goes through there, it changes the speed, and it's going to refract. As we go to air to glass, there's light going that way, it's going to bend because it refracts. So there's the light wave going in, changes direction. Then when it comes out, it changes direction. Again, we'll get more into that when we start talking about optics. And this is interesting because when James Maxwell said, light is a wave, everyone said, nonsense, light doesn't diffract. Well, there's the picture of the razor blade. Yes, it does diffract. And once they saw, oh, well, I guess it does. Maybe light is a wave. So light is electromagnetic waves. So the AM radio waves with 300 meter wavelength are electromagnetic waves. Light waves of 700 nanometers, yeah, it's pretty tiny, are also electromagnetic waves. And the nature of those waves is we have these expanding spheres as I described earlier. So one last thing I want to say about electromagnetic waves is if we produce light a different way, we can get more pure types of light. So black body radiation is going to be broad spectrum, but let's say we have a hydrogen atom. Let's put a little proton here and being orbited by an electron. Yeah, I know that's not what really happens, but we still use this Rutherford-Bohr model for atoms to explain a few things. And the height of that orbit represents a particular energy level. Well, as they often do, those electrons will sometimes spontaneously drop to a lower energy level. There's a lowest possible level, and then there's a few higher levels, and each atom has different energy levels that those electrons can be at. So it drops down to a lower energy level, and it's going to give off one little burst of electromagnetic radiation, which goes out as a sphere, as we've already decided. Now, the interesting thing about this particular quantity of electromagnetic radiation is that it's either there or it's not. It's going to depend wholly on the amount of energy released going from this level to that level. And that energy is going to have a certain color associated with it. And unlike black body radiation, which is wide spectrum, remember your black body radiation is a lot of different electrons vibrating at different speeds. This is just one jump, and it gives off one burst of energy. And so there it goes off expanding. So that's just another way of creating electromagnetic radiation. If we have a hydrogen atom and we have an electron drop from that level to that level, it's going to put out a single burst of light at a wavelength of that wavelength right there. I don't remember off the top of my head, but there's a name for it. It's called hydrogen alpha. astronomers are really interested in hydrogen alpha because there are a lot of nebula out there that have lots of hydrogen in them, and this hydrogen is constantly absorbing in energy, going up to a higher energy level, and then spontaneously drops to a lower level, and off comes a burst of hydrogen alpha radiation. And we can look at that and say, ah, yes, we know that there's hydrogen in that nebula way out there. How do we know what elements are in stars, nebulas, and galaxies? It's because of the energy coming from them comes in these bursts of different frequencies that tell us what atoms are in there. It's a little more complicated than that, and I'm not going to go deeper into it, but that hydrogen alpha tells us that there's hydrogen in that particular nebula. But the interesting thing about this packet of radiation, so let's just say that atom is right here. There's our atom. The electron drops down to the proper number of levels, gives off that burst of hydrogen alpha radiation, and it expands out in the sphere at the speed of light. I'm not showing the waves here. This is not multiple waves. It's just one burst of electromagnetic energy. It is sort of a bit of a wave because if we put a sensor right here and watch that go by, we wouldn't see that. We would see something more like this. So there are several peaks and valleys, but it's still one burst of energy, and I'm avoiding a word here that I will get to in a moment. So as that expands, it's going to encounter electrons here, there. There's electrons all over. And every time it encounters one of those electrons, there is a very tiny chance that it's going to interact with that electron and kick that electron into a higher energy state. So let's say there's an electron there, and it passes that one, nothing happens, and then when it encounters this one, it interacts, kicks that electron into a higher energy state around whatever atom it is. Does it have to be a hydrogen atom? Actually, I don't know. I'm not that deep into it. But we have that expanding sphere getting bigger and bigger. So there's our sphere of one burst of electromagnetic radiation getting bigger and bigger and bigger. And finally, it encounters something right there, and that absorbs 100% of that energy in that burst. It's gone. So there's the atom that was the source. Here's the electron that absorbed it, and here's the other electrons. But that electromagnetic radiation disappeared from everywhere instantly. Now, this is quantum mechanics according to Bob. This is the way I understand it. I am not trying to say I know something that other people don't know. This is my best understanding of the cutting edge physics as we know it now. And so I am perfectly willing to modify what I have to say if I find out that I need to modify it. But as I understand quantum mechanics, the cutting edge science, now this is the way that works. So that one package or quanta of energy expanded out, and it disappears instantly from everywhere. Now many people will say, well, yeah, that can't happen because nothing can happen faster than the speed of light. Information cannot be transmitted faster than the speed of light, but things can occur in two different places that are related instantaneously, not constrained by the speed of light. Quantum entanglement, if I understand it, is one of those things. Two objects can be created in one place and move opposite directions and be many kilometers apart, maybe light years apart, and something happens over here, the other one reacts to it because of quantum entanglement. Don't ask me to explain it further than that, but this is the understanding I have now. So that is the wave nature of a single packet of light that we call a photon. So this electron dropped to a lower energy state that created a packet of light that expanded spherically. And every time it encounters another electron, there's an infinitesimally small chance of it interacting, but it's going to pass by gazillions and gazillions of electrons. And then if it interacts with one, all that energy goes here and disappears from everywhere else. So if it reacts here, it can't react over there. It's gone. It cannot react, and it's impossible. Now, there are things that can direct this and can concentrate the probabilities. For example, a PET scan. An isotope of some sort, I don't know what it is, releases positrons, And when they interact with an electron in the patient's body, it produces two gamma rays that go in opposite directions. Well, what are those gamma rays really doing? They're really expanding. But the probabilities for one are concentrated along this line, and the probabilities for the other are concentrated along that line. And so it's extremely unlikely, almost impossible for any interaction to take place that are not along that line, and that's why they seem to go in opposite directions. Although they're really expanding as spheres, it looks like they're going in straight lines in opposite directions. And then when the detector detects two gamma rays at the same time, it can infer that those must have come from the patient and figure out exactly where in the patient they came from. So random gamma rays are not going to be considered by the equipment, only gamma rays that arrive at the sensors within the proper time frame to figure out, those came from the patient, and because of the direction they went and their arrival times, we know where they came from. And so they can scan the body that way and produce a computer picture of what's going on in that person's body. But once again, that is concentrating the probabilities along those straight lines. That is the nature of a photon. So what about the wave-particle duality? I like to explain it this way. Let's say we have a piece of photographic paper. So this is some paper coated with silver nitrate that has not been exposed to light, and we have a source of photons over here. And so, I don't know, maybe it's a whole bunch of atoms and they're producing photons, but they're traveling out in this way, and they're going to come and they're going to encounter this photographic paper. Chances are they're just going to go right on past it. But once in a while, one of these photons will interact with an electron in one of those silver nitrate crystals and change its chemistry such that they can put it in a bath and make it turn dark. And so that happened right there. And so now that photon is gone from everywhere else. So here comes another photon, and it goes right on through. But another photon comes through and it interacts over here. And once it interacts, it's gone. Can't interact anywhere else. So even though these photons are expanding spherically, they seem to be interacting randomly with different electrons in the different silver nitrate crystals in this. And over a short period of time, you can develop this and see a bunch of spots where they've interacted, or if you leave it long enough, it'll interact with enough that it will darken. Enough of those silver nitrate crystals will be encountered that it will fog the entire piece of paper. But this is what raises the idea of a photon as a particle instead of a wave, because we know it was generated here and then it reacted over here, and that must have traveled in a straight line. And then another one came here and interacted there. But some of these photons are interacting here, 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 here knows where. Well, it looks like they went that way and that way and that way. So it looks like it's a particle traveling in a straight line. But if I understand quantum physics the way I think I do, could be wrong, but I think this is the cutting edge science. It's actually coming out as a wave, and it looks like a particle because we assume that since it started there and reacted there, that it must have been a particle going in a straight line. But as I explained, it's actually an expanding sphere, and that sphere has enough energy to interact with one electron and one electron only. So when it interacts, it's gone from everywhere else. But that's the way I think I understand quantum physics as it's known today. Now, of course, Richard Feynman said, if you think you understand quantum physics, you don't. So maybe I have no idea what I'm talking about. But from what I have read and seen, I believe that is what the reality is of the particle-wave duality of light. So one other last thing to say about that. This is a little bit off topic, but the double slit experiment. Usually when you see videos about it, they're talking about electrons, but an electron has the same properties. It acts as a wave and as a particle, and so that's just as good as a photon. And the idea is that if we have a barrier with a slit in it, let's put that photographic paper here, and if we have a source of photons, so this changes the way things act such that we have the photon expanding, and it comes and hits this slit, and it's almost like there's a new source there. We get this new curve. and it's going to concentrate the probabilities in this direction. So its greatest probability is there, less, 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 and less, and less. So as these photons hit, most of them are going to not interact. They're going to do something somewhere else. But one photon comes and interacts there, another one there, another there. And we notice that we get a gradient, a very dark line here, and it gets lighter and lighter and lighter as we get further away. So the probability of interaction is concentrated along that beam, and we have a gradient of probabilities that spread out. Now let's put two slits. Let's get rid of our photographic paper. And here's our photon source, and they're going to get bigger and bigger and bigger. And guess what? That wave is going to go through both slits. And we're going to get an interference pattern. Remember, we talked about that interference. So that interference pattern is going to be such that the probabilities are going to be concentrated along, if you look at this diagram here, they're going to be concentrated along these lines here, here, and here. So what's going to happen is we're going to have interactions here, interactions here, interactions here, and interactions here, and a little bit of a gradient around each one of those. And actually, I've kind of gotten ahead of myself here because we've sent a single photon, and if we send the photons one at a time, we're going to get an interaction there, another one 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 there, and eventually we're going to get this pattern of lines from the interference. So if you see those videos, I'm kind of getting ahead of where they are, and I'm not explaining everything, but notice that when we send the single photons, they do interact with themselves because they are a wave, but that wave concentrates the probabilities, causing us to get that diffraction pattern. So each individual photon is going to go only to one place. So if we send a beam of light, we're going to get this diffraction pattern because of the many, many, many photons going through. But even one photon is going to interfere with itself. And so we would kind of expect, if the photons were a pure particle, here's my paper here, that the photons would go there and there, straight lines, but they don't. We get the interference patterns in there. So I'm probably not explaining that as clearly as I'd like. I should make a video myself on the double slit experiment. But basically, as we send a single photon, we're going to get an interference pattern, and that's going to concentrate the probabilities of where that photon interacts with an electron. And so we're going to get these lines where the photons are going to tend to concentrate themselves along those lines somewhere. So if you understand that and look at those videos about the double slit experiment, it might help you understand why the photon acts like it does. And of course those experiments say, but if you watch to see which hole the photon goes through, the whole thing collapses. Think about it. Why is that happening? How do we watch a photon? Can you watch a photon go by? No. You have to have something that's going to cause that photon to interact with an electron. So you put a photodiode there or something. The photon interacts with an electron in the photodiode, kicks it into a higher energy state, the photon's gone. So if I put a photodiode right here to detect a photon coming through that slit, what's going to happen when the photon hits that photodiode? It's gone. So the whole experiment collapses if I put a detector at each one of these to try to see which hole it goes through. So think about this when you see videos about the double slit experiment. One, the photons, they use electrons, but it works the same way. If you send single photons, you're going to get that interference pattern to concentrate where the photons are going to hit the photographic paper. If you try to detect the photon going through a slit, you're going to detect it and it disappears. And so you're not going to get the interference pattern because any photon that hits this diode is going to be gone, and so you're only going to get photons going through the other slit. So think about that when you watch videos about that. When they say, we're going to watch the photon, remember, the act of watching it, if you see it, it's gone. So just think about that when you watch those videos, and it might help you understand how the photon works in that double slit experiment. Okay, so that's the nature of electromagnetic waves all the way down to, well, we talked about signal waves and surface waves and sound waves as we worked up to what electromagnetic waves are. And then we talked about light, because the next class is going to be on optoelectronics. Now, we're going to go through a lot of this material again when we do the communications class for radio circuits, but here we did this to understand the nature of lights. So next we're going to talk about optics and look at how light works with mirrors and lenses and such to be able to manipulate the light to fall on photodetectors the way we want to. Then we're going to talk about optoelectronics, the things that produce light and the things that absorb light and detect it, in our next videos. So if you found this useful and informative, please give me a thumbs up down below. It really helps the channel and helps other people find it. And be sure to subscribe and hit that gray bell when you do so that you're notified when I put up new videos. And to study electronics technology, go to Vocademy.net and take my free course. And to help me make these videos and keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support. Or for one-time donations, you can go to paypal.me/Voced, VOCED. A big thank you to my patrons at Patreon and my one-time donors. I couldn't do this without you. And a big thanks to everyone for watching.